Hey Chem 20s, it's Mr. Jukley here again. Today we're going to talk about something that is super important for Chem 30. We're going to talk about titrations. So when we do titrations, essentially what we're looking at is we're trying to figure out, well, let's go back a second. Essentially what we're looking at is we're looking at solution stoichiometry, but in the lab. That's a good way to put it. Good way to put it. So solution stoichiometry in the lab. So if you can do solution stoichiometry, you can pretty much do a titration as long as you are following a couple steps and following those things. So unfortunately, we won't be able to go through and do an actual one using the specific glassware, but I still think I'll be able to do a pretty good job showing you what's up here. So essentially what we look at, a titration is a common experimental design used to determine the concentration of something. Right, so you don't know the concentration of something, you can do a titration to figure it out. It involves adding a carefully measured amount of a solution of a known concentration called a titrant. Now I know that this is like a huge block of writing, so there's sort of two different things, two different definitions that we'll add to this. The titrant is the thing that you know the concentration of. So I'm going to abbreviate concentration like this. So the titrant is the thing you are really, really, really good, and you really know, I spelled titrant wrong somehow, the concentration of that. Typically, that's our standard solution, right? So we've mentioned that before. We know how to build standard solutions. Now we're going to use one of those standard solutions. So I'm even going to add that standard solution. I'm going very, very shorthand here. What we want to do is we want to figure out the concentration of the sample. Now, sometimes you get some confusing language, especially on the internet. So the sample is your unknown concentration, abbreviated like that again. The sample is also sometimes known as your wow, good spelling today, Mr. Jukley. Nailing it. Is sometimes known as your titrand. So notice the difference, titrand versus titrant. Kind of annoying, but you'll probably run into that if you go somewhere. Now, our notes are a little tiny bit misleading. Where it says the burette, which the burette, I'll show you a better thing. It's a long, skinny tube, essentially, with a valve called a stopcock at the bottom, with increments on it, so you can accurately measure how much of a substance leaves it. We've also got an Erlenmeyer flask at the bottom. Now, this is misleading because it says the burette contains the titrant, and the flask, actually, Erlenmeyer flask, contains the sample. But it doesn't really matter what goes where, as long as you're very, very good and you're very clear on the amounts that go into each, so the volumes that go into each. So again, it doesn't really matter what goes where. And we'll look at that as we go through and check out a couple different things here. So to perform a titration, we essentially want to fill up the burette. I'm going to stick with the titrants, but remember we just talked about it doesn't really matter. We want to place the sample inside of an Erlenmeyer flask, and we want to add an appropriate indicator. So what we're doing in Chem 20 is we're doing pretty much exclusively acid-base titrations, which makes our indicators fairly simple. We've seen those indicators before. We know the indicators. Where did my data booklet go? They are on page, oh boy, I should have done this before. They are on page 10 of our data booklet, page 10. So we got a good idea of those indicators. Those indicators will help determine the equivalence point. So the equivalence point is the exact place where, in our case, all of the acid has reacted perfectly with all of the base, and we have it at a exact exact pH of 7. That's in our case because we're doing strong acids and strong bases. When you get to Chem 30, it'll be a little bit different. So this shows us, this equivalence point shows us exactly where all the acid and all the bases have reacted in perfect stoichiometric amounts. What the indicator shows us is the end point, which is the color change that corresponds to that. So you need your indicator to be in the equivalence point, and we'll talk more about that when we get to the graphs and we get to the big ideas here. So essentially, We open up the stopcock. That's this little valve that lets stuff out of our burette. So we open that up, and we slowly add the titrant to the sample. We slowly add it. Now the first one typically goes really, really fast. We get to a point where we see that end point, so we see the color change. We make note of how much of that titrant we have added to our sample, and we can go through and do it again, and do it again, and do it again. But in the following couple things, we really, really, really want to slow down to the point where we're going drop by drop by drop, because we do not want to overshoot the end point, right? If you add even half a milliliter too much, it's too much that you're adding. Okay, we want to record the final volume. We want to make sure we understand, and what we need is 3 trials within 0.2 milliliters of each other. So the first trial that we go quick on usually isn't really what we're looking for, but we need 3 trials within 0.2 milliliters of each other. Once we have those 3 trials, we want to average the volumes of those 3 trials and discard any that don't fall in the right one. And then all we're really doing after that is a stoichiometric calculation. Stoichiometric calculation. Cool. So those are sort of the ideas, and I realize that we ripped through that. So we're going to slow down a little bit here. I'm going to open up a couple different things, and you can actually open this up as well. So all I did, go on your web browser. You can check this out at the exact same time. All I did was I typed in OK state. I don't know if I can write on this. I definitely can't. OK state virtual titration. Go over to my computer here, and it's this very, very, very first one. Let's click on that, and this pops up. So this is the screen that we want. So again, I Google searched OK state virtual titration. Go back, there we go, and it's just the first thing that shows up will get us to that titration. Now I've got one here, and I've got a blank sheet there. Perfect. Okay, so let's set this up together a little bit here. I gotta run a little bit back to the computer. So we want to determine the molarity of an acid or a base solution. So that's the goal of a titration. We've got our burette here with our stopcock there, and we've got our Erlenmeyer flask that's currently empty, and it's got a magnetic stir. If we're doing this in the lab, we typically have to do it with our hands. So let's see. Let's go through. We're going to go through and we're going to talk about select the type of reaction. So step 1, we want a strong acid versus a strong base. Step 2, fill the burette with either an acid or a base. It doesn't really matter which. So I'm going to choose acid for this one. Acid. Nice. Step 3, and this is kind of hard to follow, but step 3, select the acid and the base. Okay, so I'm going to select classic hydrochloric acid. So the acid is going in the burette, and you just saw that fill up. So the acid, hydrochloric acid, is in the burette. And I'm going to select, classic sodium hydroxide. So I'm going to put the sodium hydroxide, and that's going to go into my Erlenmeyer flask. You might not be able to see this on your screen, but if you're following along, you can do that there. So some things to note with this is we have added sodium hydroxide to the Erlenmeyer flask. It tells us the exact molarity. So that's 0.991 moles per liter of that sodium hydroxide. And we've got exactly 25 milliliters of it. Now yours, when you click on this, it's going to give you different ones. Like every time that I do this, so if I reset this, same thing, strong acid, acid over there, hydrochloric acid, sodium hydroxide, it gives me a different value. So you can use this to practice over and over and over and over again, right? Tons and tons and tons of times. Perfect. So we've got our acid in the burette. We've got our base in the Erlenmeyer flask. I need to select an indicator. I'm going to select bromothymol blue. And if we look at the pH range for bromothymol blue, I believe it's 6 to 7.6. And if we're using a strong acid and a strong base, when they neutralize each other, they should have a pH of 7. So bromothymol blue is directly between that 6 to 7. Awesome. Okay. Now what I want to do is we want to start to add our acid to our base. Start to add our acid to our base. So I could add this dropwise, but that is going to take forever. So what I'm going to do is it says push the slider up and add a volume of acid. So I'm going to push this up. I'm just going to randomly try 5.5 milliliters. So I added 5.5 milliliters and there was no change to my indicator color. I'm going to push that up to 7. No change. Push that up to 8.5. No change. 9. Nope. 10.5. Nope. 12.5. I don't want to do too big of a jump. 14.5. No change. Excellent. No change yet. Be patient here. We're gradually sliding this thing up. Oh, 21. Somewhere between 18 and 21 milliliters gave us the change that we were looking for. So I'm just going to write that down. 18 to 21 milliliters. Holy crow. So that kind of got us to an area where we're sort of close. That's a huge range though. 3 milliliters is what we're looking at. So let me I'm going to put this on pause and see. Okay, I didn't screw it up, which is nice. So what I did to reset it was I just pushed this concordant values buttons, and then I have the same molarity, the same volume. I've got the same, I don't do everything, just don't push reset, right? Then you have to redo everything, including, you know, your volumes that you're looking at. So it was somewhere between 18 and 21 milliliters, so I'm just gonna skip right ahead. I'm gonna try it with 18.5 milliliters. Notice that the color didn't change. Now I'm gonna add it really slow. I'm going to add it drop-wise. So 1 drop at a time until we see that color change. And this is exactly what we would be doing in the lab. Oh, I think I added 1 drop too many there even. So let's get rid of this range. So our first trial, we had 19.4 milliliters of acid that's been added. Okay, let's try that again. So now I think we're a little bit more accurate. I might be able to skip up to 19. So notice I added 19 and no change. So I'm looking for 0.4 milliliters. And we're just going to go drop by drop by drop. I realize now talking like that might be putting you to sleep. Apologies. So we're at 19.3. Oh, there it is. 19.36 is, I think, what we're looking at. 19.36 milliliters for our second trial. Okay, let's do one more. So we have 3 trials within 0.2 milliliters. So let's jump right back up to 19 milliliters, and then we'll start adding it dropwise. I can go quite a bit quicker now, because I know approximately what I'm expecting. There it is, 19.36. I have a feeling if I did another trial, it would be 19.36 one more time. Now, if you're following along and you're doing this, you would have different values, right? Because they change every single time. Okay, but we've got this. Like we just did the main part, the lab part of the titration. All that's really left to do now is to do the math and figure out the concentration of, let's see, the acid. So we're trying to figure out the concentration of the acid, because I know down at the bottom again here, I know the molarity of the base, I know the volume of the base. So if this is just a, let's just go through and check this out. My average, you know what, I'm going to ditch that one. I'm just going to say when I add up 19.36 plus 19.36 plus 19.36 and divide by 3, 19.36 milliliters is what we've got there. So just like every stoichiometric calculation, it starts with a balanced chemical equation. So I am reacting hydrochloric acid with sodium hydroxide, and I'm going to go ahead and produce, let's see, so it's going to be NaCl and water. And I'll just include states. And do I need to balance this even? No, right? It's 1-to-1 ratios everywhere, so no need to balance. Let's summarize some of the things that we've got. So our goal is to figure out the concentration of hydrochloric acid. So I'm just going to put that there. Things that I know about the hydrochloric acid, I know that it is a volume of 19.36 milliliters. I might go ahead and change that into 0.01936 liters, just so it matches a little bit. Other things that I know, let's see, back from the website here, I know that my molarity of the base is 0.1628 moles per liter. And again, I'm just getting that right off the website there. And I know that I had 25 milliliters, which I'm going to change to 0.025 liters. Cool. From here, like now this is legitimately just stoichiometry. So we've got our balanced chemical equation. We need to find the moles of something. So we're given enough information about sodium hydroxide to figure out the moles of sodium hydroxide. So I'm going to start with 0.025 liters of NaOH. I'm going to multiply that by, let's see, I want moles, NaOH, for every liter of NaOH. So let's see, it is 0.1628, that's 6 didn't work, 1628 moles for every 1 liter. I see liters, canceling with liters, perfect. Next, so I just figured out the moles of sodium hydroxide. Now I want to figure out the moles of hydrochloric acid. Okay, so let's see. I need moles HCl on the top, and I'm going to need the moles of NaOH, my strong base on the bottom, so that moles of sodium hydroxide cancel with moles of sodium hydroxide. This is super easy. It is a 1-to-1 ratio. So now, if I just look at the units that I've left, all I have left is moles of hydrochloric acid, which is great. We are almost there. We want the concentration. So the concentration is always in moles per liter. So I got moles on the top. I just need liters on the bottom. And of course, that is liters of HCl. Awesome, liters of HCl. And then I'd go through and I'd say, okay, well, how many liters of hydrochloric acid did I actually have? Well, it is 0.01936. Holy mackerel, that just barely had enough space. And I need a placeholder in the top, so I'm just going to put my placeholder right up. Alrighty, so I had to get out the calculator there, but let's plug the numbers in. So I got 0.025 times 0.1628 times 1 over 1, I'm not even going to add that, times 1 divided by 0.01936, and let's see, we end up with a concentration of 0.0, nope, extra 0 in there. Let's go back a second. So 0.2102 moles per liter. So our concentration of HCl is 0.2102. Let's see if we can figure out some sig digs here, actually. Let's go back to here. So I got, let's see, 4 sig digs for my bases. And I think I have 4 sig digs. So yeah, 4 sig digs should be good. Okay, moment of truth here. I haven't actually tried this out yet. But let's see if we can figure out. So all I'm going to do is plug that concentration 0.2102. Okay, moment of truth. Correct, we did it. I wonder what the graph's going to look like. Oh, this is beautiful. I actually haven't got this far in this one yet. So notice what our graph looks like. This is actually the next thing that I wanted to talk to you about in our notes. So this could not be in a better place. Absolutely could not be in a better place. So I just can't see the whole thing for some reason. It's cut off on the side. So what this is showing us on the side, or what it should show us over here, is our pH of the solution. And we started with a base, and we are measuring with this. How do I return, there we go. We are measuring the pH inside of the Erlenmeyer flask. So it makes sense. If it starts with a base, it starts with a really, really strong base. Perfect. And then we gradually add some acid, but it stays at a base. That's actually called a buffer when something doesn't really change its pH, right? So it's changing gradually, but I add some acid, it pretty much stays the same way. Add some more acid, pretty much the same way. And then look what happens. We get this super, super, super ridiculously steep area. And then it goes back to being a buffer, but now it's a buffer for the acid. So it's got a low pH over here, it's an acid. Right in the center of this steep part is our equivalence point, where the acid has matched the base. All of the hydronium has matched with the hydroxide, and we end up with a neutral pH of 7. Perfect. And then our indicator just needs to be somewhere on this steep part of the graph. So our indicator needs to be kind of in the middle right here, which bromothymol blue, again, between 6 and 7.6, should be right in the middle of that, which is perfect. Cool. So titrations, I mean, there's a little bit new definitions, right? A couple new definitions. But once you get down to it, once you get over the actual process of this, it's realistically just solution stoichiometry, which is awesome. So there's this that you can play with a whole bunch of times. Let me go back to the notes here a little bit. So I don't know if I'm going to necessarily go through full examples of this with you, because we just went through a full example. But let's see, where did I put my felt pen? There it is. It's in my pocket. Go figure. So as I go through and as I look at this, the things that are a little bit different from the thing that we just looked at, that app that we just looked at, is let's see, our description. The titration of 10 milliliters of CH3COOH with 0.202 mole per liter sodium hydroxide. Okay, so there's some hints in our diagrams here. So my final Buret reading and my initial Buret reading, well, if I ever want the volume, so our change in volume, well, that's just our final volume minus our initial volume. So that's actually set up. So if I wanted to go through, I do my final volume minus my initial volume. So that's going to give me, let's see, in this case, 14.1 milliliters. So that's not so bad. If I do this one, 26.9 minus 13.9, oh, that's easy math, exactly 13.0 milliliters. The next one, trial 3, 12.9 milliliters. And then finally, 13.1 milliliters. Okay, so that's good. One thing that this notes, this tells us the volume of sodium hydroxide. So I know the volume of sodium hydroxide. I know the concentration of sodium hydroxide. That sounds like it's going to be my known. But I need to choose 3 of these that are within 0.2 milliliters of each other. So 14.1, I'm not going to choose that. But 13, 12.9, and 13.1 are all within 0.2 milliliters. So I'm going to use those. And I'm going to say that my average for this is equal to 13.1 milliliters of sodium hydroxide. Now, as I go through, I need, and again, I'm not going to necessarily do the whole thing for you, but I'm going to help you get this one set up a little bit here. I'm going to go through and write my balanced chemical equation. So CH3COOH plus, what are we using? Sodium hydroxide, NaOH. And we know that this is a neutralization reaction, so it's going to create, let's see, water, and then whatever salt is left over, in this case it's going to be NaCH3COO, and of course that's going to be aqueous. Then I need to summarize the information. I think that's probably one of the harder parts from this, is just summarizing all the information that we've got. So let's see. It's the titration of 10 milliliters of CH3COOH. So I know that this volume is going to be equal to 0.01 liters. Let's see, my sodium hydroxide is going to be, let's see, 0.202 moles per liter. And we just figured out that the volume of sodium hydroxide has an average of, let's see, 0.013 liters, or 13 milliliters. Now let's look at the question. What is the concentration of acetic acid? So concentration is a question mark. And from here, it's, again, it's literally just stoichiometry. It's just solution stoichiometry. So we can do this, absolutely. And all of these first three examples, which I'm going to leave actually as a bit of practice for you, same thing over and over and over again. Okay, this is kind of what we talked about quickly, so I'll just spend a very quick, maybe 2 minutes going through and talking about this. So a pH curve is the graph that shows us the pH versus the volume of, in this case, I guess, sodium hydroxide that is being added. So for a monoprotic acid-base reaction, we see one of these steep bits, right? And if it's a strong acid and a strong base, that equivalence point, so equivalence point should be at a pH of 7. But if I had a polyprotic substance, remember polyprotic means more than one hydrogen, it actually reacts twice. So you get one steep area here and another steep area there, right? That's more of a Chem 30 thing, so we'll leave that for Chem 30. We're dealing with monoprotic. So things that we want to look at here are buffer regions. So I already kind of mentioned this. Our buffer regions are areas that don't really change in pH very much. So I got a buffer region here. I'm going to put B for buffer, and I got a buffer region here. So we're adding quite a bit of sodium hydroxide to this acid, whatever it is, and the pH isn't really changing much. But then all of a sudden, we're not in a buffer region. The pH, you add a tiny bit of sodium hydroxide, so just a tiny bit here, and it changes drastically. So again, they're relatively flat regions, right, our buffer regions, and buffer is a substance that resists a change in pH. So they're flat because they're resisting the change in pH. So common buffers that we often see are acetic acid and acetate. They're frequently used in labs. H2CO3 and HCO3, this is actually found inside of your system. It keeps your blood at a pH of 7.4. So even if you get a bit of acid in your blood, or it becomes a bit more acid, the buffer system will take care of it. It will keep it relatively constant. Our endpoint, the next thing that we want to talk about, as our endpoint is the visible end of your titration. So I'm just going to fill this in. I don't really necessarily need to read this entire thing, but it's the physical endpoint. It shows the actual change of the indicator's color. So there, for all endpoints for us are visible, and I'm going to put color change for us because we're using indicators that use color. Just note that it's not always at a pH of 7. I mean, for us with strong acids and strong bases, it will be, but if you use a weak acid, a weak base, a monoprotic, or sorry, a polyprotic, it might not necessarily be at 7. Okay, your equivalence point, we already kind of talked about this. It's where the titration is technically over, but it's the balanced chemical equation. So it's where exactly we have the right amount of acid matching with exactly the right amount of base. And finally, what do we have here? Something important for us, the type of reaction taking place. You do need to recognize what is reacting with what and what goes where. So as an example, in this one right here, it looks like I'm starting with a base, and I know that I'm starting with a base because it's got a really, really high pH. So that is the base that is in my Erlenmeyer flask. And that means that in my puree, I'm a really good drawer. We have to have our acid. So we're adding acid drop by drop by drop to the base. And we notice with this, I'll highlight in green, we're starting, there's our buffer region. We're starting with a really high pH. All of a sudden it drops. So I'm going to highlight that in red. It's the steep drop part. Highlighted in red, and then we get back to another buffer region, which in this case I'll draw in black. It's a buffer region, but now it's an acid. So we've added enough of this acid into there that all of the base is gone, and now it is just acid in there with a really, really low pH. Again, our equivalence point is the dead center of that steep part. For us, it's going to be a pH of 7. And then all we really need for our indicator, when we're choosing an indicator, it should be in that steep part. The change should be in that steep steep part, and it should be as close to the equivalence point as possible. So for us, as close to 7 as possible. Just to finish it off, since the initial pH is 7, this indicates that what did I write down here? I think it indicates that the Erlenmeyer flask contains the base, and the Burette contains the acid for this particular graph and this particular titration. Okay, so there's a little tiny bit more. I'm going to make a separate video of it here because this one's getting kind of long. Practice for this is those couple questions. So practice, and this is just for the mathy part. Practice for this is on page 14. So there's a couple of them on page 14. And then there are, let's see, questions, I believe it's 1 to 7 on page 19 to 22. And again, this is one of those things that, do it until you're comfortable with it. Do it until you're understanding it. I do have to post a new answer key on our Google Classroom. I realize the old one's kind of out of order and kind of crummy, especially for this part. Like we kind of got by for the first bit, but I'll post a new answer key on Google Classroom right away here. Check it out there. But yeah, make sure you practice. Okay, one more video. I promise the next video is going to be super short and hopefully less rambly for this. It's all about picking an indicator. Okay, bye for now, Chem 20s. We'll talk to you again soon.